We have with us Professor Satyam Suwas from the Indian Institute of Sciences, who will be talking regarding the role of academia in sustained growth of additive manufacturing.
Hello, everybody. I am Satyam Suwas. I am a professor at Indian Institute of Science, Bangalore, in the Department of Materials Engineering. I am also a faculty in Center for Product Design and Manufacturing and Interdisciplinary Center for Energy Research. Today, I'm going to talk about the role of academia in sustained growth of additive manufacturing. This presentation is based on the contributions from Dr. R.V.S. Prasad, Mr. R.J. Vikram, Mr. Deepak Kumar, Mr. Sumit Bahal, Mr. S.K. Gupta, and Professor Kaushik Chatterjee, who have been my collaborators and students in some sense. So in this presentation, I am going to take you through the entire process of additive manufacturing. Though this might have been told by other speakers, I would like to introduce this topic by myself because I have to bring out certain issues that really need attention in the process. So to begin with, as I understand, additive manufacturing is a method of manufacturing parts from powder, wires, and sheets, layer by layer. So this is a bottom-up process, bottom to top process. The process can be done by melting as well as in a solid state manner. There are solid state variants which are, although not very popular, but they may come soon into existence. The main claim to fame of this process is a complex part can be formed in a customized manner directly from design without the need of expensive tooling as required for conventional manufacturing. The process is near net shape process. In metallurgical engineering, we classify such processes into near net shape processing, where you can directly get to the final component from the elemental constituent or the primary constituents of the process. However, even though it does the same thing or it is intended to do the same thing which conventional manufacturing does, there are certain differences in conventional and additively manufactured parts which requires a lot of attention because these parts are supposed to replace the components which are already into existence. The important highlights are the existence of mechanical anisotropy, microstructural features, and residual stresses present in the material, and of course, nonetheless, defect structures. So I have shown here two pictures. One is of biomedical implant. This is an area where additive manufacturing is very popular, and this figure shows jaw implant, which is made of titanium alloys. And the other one shows an aerospace component, which is a compressor blade, again made of titanium alloy, or it can also be made with cobalt chrome alloys. So these two sectors are the main subscribers of additive manufacturing concept. The first one precisely because here one can custom build the product. Like somebody's bone may be different from somebody else's bone, and if there is a replacement to be done, one can simply take a picture and make the part as per the requirement of that particular patient. Similarly, in the aerospace sector, the components can be fabricated in an integrated manner. So normally in a conventional process, one needs to have several components and they have to be joined together. While in additive manufacturing, these steps can be eliminated and one can get the component as a whole. This has advantages like it has freedom of design, complexity for free, you don't pay for it. You can make complex components as simply as you can make simpler components. There is elimination of tooling, and of course lightweight design one can make because one can always tailor sections with desired properties. Production steps are minimal as you directly go to the desired products, but it also has disadvantages that the build rates are slow, so the high productivity is not there. Considerable efforts are required to get optimal microstructures. Then there is this is a discontinuous production process, unlike many processes which are already made continuous by the industry. Of course, this can be improved. It can be made a continuous process once a process chain is established. So far, this is limited to smaller components, but it can again change with the increased capacity of laser, increased machinery, which can involve more than one laser or more than one source for melting. And of course, powder availability is a big challenge because as of now, the understanding is only a certain type of powders are suitable for additive manufacturing. Now, coming back to the processes, we have two types of processes in terms of the nature of tooling or nature of the equipments. One is directed energy deposition based processes, where powder is fed and from a hopper, and then it goes, melts and forms a structure by a laser. In other cases, one makes a powder bed and melts it either by laser or electron beam, and the particular shape is given. The laser or electron beam traverses as per the shape guided by the designer. So these are the two variants of the process, two major variants of the process. And the first one can be used as a laser as well as with electron beam, though the laser one is more popular so far. And the first one also has an advantage that one can feed it with wire as well as with powder. Wires have another attributes that one can use large parts. One can use the wires for fabricating large parts from this technique. There are various process parameters which influence the whole process. The most important is feedstock quality, that is the type of powders, and that includes the shape of powder, size distribution, surface morphology, composition, internal porosity. All these decides flowability of powder and as well as the apparent density of the powder. And these are governed by the way powders are made. If they are made by gas atomization or rotary atomization, the two most common and cheaper ways of making powders, the powders may have irregular shape and satellite formation, while if one uses some advanced techniques like plasma rotating electrode process or plasma atomization, then one can get better quality of powder. However, the process adds to the cost. Now, there is a important attribute to the powder making itself. If the process involves entrapment of gas inside the powders, this whole thing can lead to final porosity in the product. Energy sources can be of different types. Laser is the main source. Generally, electron beam is also source. And the parameters like energy density, laser power, hatch distance, layer thickness of powder, and scan speed all contribute to the whole process or the products. I have shown here some examples of different types of powders. This is the powder with a satellite formation, and this is a powder with elongated ellipsoid morphology. Both these are not good for close packing of powder bed. What is important is the third type, where there are spherical powders of desired shape or size distribution, and these are the most suitable for additive manufacturing in the most efficient way, where defects are not there. But one thing I must bring into consideration, that powder characterization is important. If one sees through optical microscope, all these powders look very similar as shown in the third column here. But if one sees with electron microscope, the differences are very apparent in this case for both the types of powders. The other parameters are how do we traverse the laser scan. So either we can do it in unidirectional manner, bidirectional manner, or we can give to any shape to this process. So this also influences lots of properties of the product, which I will show in the next few slides. The optimization of these process parameters are very important, and these optimizations basically involve controlling beam power and scan speed primarily, and the effects are very apparent in the bottom pictures. Here it is shown that if we increase the scanning speed, the porosity is increasing here in this case, while if one increases the laser power, the porosity decreases. So these are important parameters, and people have constructed a map of beam power versus scan speed, and there is a safe zone in between that leads to the product with optimal porosity content or least porosity content. On either side of it is not desirable. In one side you get keyhole defects, other side one can get unmelted particles. So it is important to prepare such kind of a map where one gets to optimize both the parameters, techno commercially see the feasibility, so that one get densest component possible. Porosities can occur in two ways. Either they could be a result of insufficient energy or excessive energy. Both are dangerous. So one has to really optimize energy content in a very subtle way. And one can have, the first type can lead to unmelted particles as shown in this case. And the second type can lead to keyhole defects, which were shown on the other side of the map that I had shown in the previous slide. So both are dangerous. So one has to avoid in both sides. So one has to remain an optimal choice, or one has to keep an optimal choice of parameters that leads to uh, least porosity or least amount of defects. Another types of defects are cracking, which comes as a result of solidification and subsequent heating because the material goes through high levels of temperature fluctuations. Swelling can come in, residual stresses come in, and there are strategies to mitigate all these things by increasing substrate temperature, shorter deposition length, or scanning in smaller islands. All these things are possible, but again, all these things have to be weighed against process feasibility. So it just opens up a plethora of topics to study for particularly those who are in academia like me. One can really work on various process parameters that gives optimal combination of parameters that leads to minimum amount of defects. Another important optimization that is required is microstructure, which is a function of temperature gradient during the process and growth rate. Here again, one can have a choice of parameters or window of choice of parameters where one can get structures starting from equiax, dendritic, columnar dendritic, cellular to planar. So this leads to all kinds of microstructures which are suitable for different types of mechanical properties. Like equiax microstructure is very good for optimal combination of strength and ductility at room temperature. So here in this slide, I am showing the complexity and interaction of various parameters, and I won't emphasize too much about this, but one can see that there are many intertwined issues in this, where the additive manufacturing software and part geometry, scan strategy, AM hardware, build chamber, atmosphere, and feedstock quality all influence various outcomes, and then finally they all influence whether the component is suitable or they fail. A particular combination leads to a suitable mechanical properties, what are the feature sizes and suitability for a particular application. We carried out some research, which in a few minutes I will tell you. We changed some of these parameters, and this is a typical representative of that. So this was grown in a lab scale where we have deposited the material in a different way. This is for 316L stainless steel, and we have seen that the different methods of deposition leads to different types of microstructural features. So the main important concern here is these microstructural features are characterized by different properties. Like for example, a vertical built material has shown a different stress strain curve than a horizontal built material, and both of them are different from conventionally built material of 316L stainless steel. So in one case you have a good ductility, in one case you have poor ductility but higher strength. So one has to really optimize the parameters as per the requirement. There is another variation one can bring in is head style and head rotation. We also played with these parameters and ended up in different types of microstructures, and again different types of properties. And properties are so much different that it's about, say, the strength levels could vary from 750 MPa to 1000 MPa. So it's a clear-cut improvement or loss of 25% of the properties. Ductilities were same in this case, but ductilities were tested under compression, so the material didn't fail up to this level of strain. But suppose something is subjected to tensile loading, then it could have a different result. Well, the post-processing strategy is very important. Heat treatments can be designed, and again, heat treatment has profound effect on the properties of the material. Heat treatments lead to changes in microstructure, and they have an important bearing on all kinds of room temperature and high temperature properties. Now, the last part of application, I will tell you about the bone plates, which are important component, and we have a case study here. Bone plates can be made in different shapes, as it is shown here. And the property requirements are elastic, lower elastic modulus, which can match with the bone. And material choice is, of course, here for Ti64, which is a very suitable material for these applications. And then we printed the bone plates, and we tried to see whether these bone plates are similar to what properties which we expect, right? By the way, this is also a very big market of about 16 billion in 2021. It's likely to be over 16 billion in 2021. So by doing heat treatment of printed structures, we generated different types of microstructures, and we saw there is huge difference in hardness or strength. Additively manufactured material has shown higher hardness, and then other mechanical behavior can be shown by tensile test and 3-point bending test. Here WR shows WR shows the wrought material which is conventionally used, and additively manufactured material shows this black one here, AM material. And we could see that the properties are different, but after heat treatment, we can get similar level of properties as your wrought material. So as additively manufactured parts are not very suitable. So far, I can enumerate the challenges which metal additive manufacturing industry has, and for which there is a need for a strong industry academic collaboration. The major issues to be tackled is porosity and residual stresses, which are detrimental for components which are supposed to be loaded, whether under uniaxial loading or in cyclic loading. So this is very important, and this requires a very careful study of process parameters that could lead to optimal porosity and optimization of residual stresses. This can primarily be done either by substrate heating, or this can also be done by optimizing the post-build heat treatment. Another important point is non-equilibrium microstructures, textures, interfaces, and compositional issues, compositional variation, which can be addressed. And there is the technical challenges are extremely high localized temperature gradients and the fast moving heat source that leads to some of these issues mentioned above. And of course, the gas liquid, gas solid, solid liquid interactions, fast heat and mass transfer and phase transformations, rapid solidification, all these issues they make the whole thing complicated, and these need to be addressed. Another important point is, as I mentioned in the beginning of my presentation, that these components made by additive manufacturing do not exhibit the same property as the conventionally manufactured parts. So one needs to qualify, or one needs to evolve a criteria for qualification of these parts. What are the acceptable limits? And then recommendations have to be made for post-processing conditions. Then recommendations have to be made. What are the optimal choices for initial feedback, or initial feedback in terms of parameters, feedstock? All these things are to be said through an academic study, can be brought in. And production rates and robust processes have to be developed and designed. Production rates have to be tuned, and robust processes have to be designed. So here I have just shown through a diagram that composition, powder, process, post-processing, and they all lead to the optimal properties, and they all rest on the two parameters. One is process engineering, another one is material and process interaction. The most important thing takeaway for this industry and academic collaboration is, being a multidisciplinary field, one needs to understand mechanical design and material property in addition to machine details. So generally, shop floor engineers are made aware of these two aspects, because one specializes in one area, one specializes either in mechanical design or materials aspect. So either there has to be a team that can address, or somebody should get this information and interpret and feed into the operation part of it. Then the data has to be generated quite substantially, because as I said, I have shown some diagrams, conditions, choice of optimal parameters, all that is required that can feed into the optimal design of products. So there has to be a very strong database. Then there has to be domestic value addition in core and ancillary components, machines, materials, and software in AM, because we can't completely depend on things that we import from other places. This is applicable to any country, that one has to tailor the whole thing as per the domestic value addition. Then, of course, the linked part is import dependency has to be reduced by developing local skills, technology, scale of production. Innovation has to be promoted. This is what I have presented is based on the existing machines, but definitely, since it's an ever-growing field, one has to bring in innovation in terms of machinery and research infrastructure, and commercialization of end-user application based on industrial AM products as suited for domestic and global markets. And one has to really create and update innovation roadmaps for AM technologies and strengthen collaboration with global AM organization and innovation and research centers, either local or global. So these are some of the important points. If I summarize, immediate needs are feedstock optimization, process optimization to minimize defects, to optimize microstructure. A complete database is required for this. Geometry optimization is required, particularly a combination of geometry, process, and composition. Screening of materials is required, choice and scatter of composition, how much scatter one can tolerate for a particular application. Post-processing strategies have to be optimized. That means heat treatment guidelines have to evolve. And property database has to come up. What are the properties for AM products like tensile, fatigue, fracture toughness, high strain rate response, thermal stability, environmental susceptibility, chemical and biological response, if they are desired to certain applications. Well, with this, I complete my presentation. My acknowledgements are for all my students who contribute to AM research, all collaborators, all funding agencies. Thank you very much.
Thank you for the amazing session. It was really insightful. Hope you have learned a lot from this session.